Okay, so let's get started. A couple of things on housekeeping. So we're getting closer and closer to our celebration next week. So I wanted to sort of square some things away with that and make sure everybody has a good idea of the plan moving forward, not just through the second exam, but to the end, because we're actually getting kind of close to the end. I mean, I was sitting here up here, it's week 10, you know. Damn. I think that's the only thing to say. So let's start off with immediate housekeeping, and then let's move forward to more long-term housekeeping, because I got a couple further announcements. First off, in terms of this class, so homework number 4, you all have submitted homework number 4. The solution is on Blackboard. Okay, we haven't got it graded. My goal is to get that to you on Thursday. Okay, homework number 5 is due Thursday. Okay, now. Look what happens on Thursday. We do our exam review, and then next Tuesday we have our second exam. So because of that, on Thursday I am giving you the solution to homework 5 on Thursday. So this is going to be the same deal like it was before. Those homeworks, I'm going to have a tough time accepting a late homework since you have the solution. Okay, so please don't wait and turn that in late. Turn that in on time. Okay. So today we're going to talk about beam deflection. Thursday we have our exam review, and then next week we have our exam. Let me be absolutely crystal clear. Beam deflection is not on the exam, okay? It's not, okay? The exam covers geometric properties, it covers shear and moment diagrams, it covers bending stresses, and it covers transverse shear stresses. That's the exam, okay? So composite beams, all that stuff. So, but no beam deflection stuff. And you know, I've wrestled with whether or not to put beam deflection on this exam, because I've taught this class a number of times before. Honestly, I just think it's too much for an exam. I think there's just too much material, and I'd rather, while it does sort of make sense to put this along with beams, I just think it's a lot, and I'd rather just parse it or split it up a little differently, just to, you know, give you all some relaxation. I could put beam deflection on the final, where you all have 2 solid hours to do it, and you got plenty of time. So I think that's a little bit more fair to you. Everybody okay with this? Okay. Any questions? All right. Now, let's deal with, before we get into topics, let's deal with the schedule moving forward past this exam, because I need to mention here on Tuesday, October 23rd. I cannot believe this whole time we are still on schedule, because with everything going on, it's Tuesday, October 23rd, and we are talking about beam deflections. I can't believe we're rocking and rolling there. Okay, so today we're talking about beam deflections, and then we have our exam review and the exam. We'll pick up beam deflections when we get back, and then there's Tuesday, November 6th. On Tuesday, November 6th, I don't think I'm going to be here. If everything goes the way I think it's going to go, I've got a research trip going on. I've got a field test that I'm doing on a bridge in Ohio, and I'm not going to be here this Tuesday, okay? So what we'll probably do is this, okay? We'll take this lecture, this combined loading lecture, and these 2 combined loading lectures, and shift them down to do that Thursday, November 8th and Tuesday, November 13th. I do not want to do those lectures online, okay? I have in the past said, you know, I'll record a video and you all watch it, and that'll be our lecture. Of all of the lectures that we have in this class and of all of the concepts, this is probably the one that, I don't want to say it's the trickiest, but you really got to pay attention, because basically what we're doing here is what happens if you have multiple stresses going on all at once. So it's kind of an important lecture, okay? So what we've got is that, and then we have a combined loading part 3 and 4, which is number 1, it's split up by Thanksgiving break, and 2, they're sort of independent topics. So here's what I think I'm going to do for this lecture. So like I said, these 2 are going to shift down. So what about this one? This beams and frames example, I think I'm going to turn that one into an online lecture. I'm just going to post a video. The reason why is because all I'm doing is taking the sigma equals my over I stuff and the tau equals VQ over IB stuff and just sort of like redoing it with more circle. And I don't think it's really necessary for us to be in here in class to do this one. I think I can record this. And I'll be honest, there's another reason I'm doing this. If you look at the schedule, I listed a makeup day right before Thanksgiving break because I was going to give you all that day off, okay? You know, unless you all want to be here at 8 o'clock in the morning the day before Thanksgiving break. Now we get vocal. I think this one's one that I can post a quick video on and do this, and then I'll still give you that day off. But this one, we kind of need to be in class for, the thin-walled pressure vessels. That one we kind of need to be together for. And then once we finish thin-walled pressure vessels after Thanksgiving break, the only thing we have left is column buckling, and we're done. That is mechanics of deformable bodies, period. So, so yeah, I wanted to give you sort of a, this is it. This is where we're at, okay? Any questions? So like I said, go ahead and put in your schedule that until you hear from me otherwise, we're not going to meet on Tuesday, November 6th. We'll meet on the 8th and the 13th. Probably do an online lecture for this, and we'll still cancel like physical lecture on the 15th. Sound good? All right. Okay, so one other thing that I'll mention has absolutely nothing to do with this class, but the spring schedule is out. Here or something on the floor. Oh, there's no trash can. Oh, there we go. I'm going to miss this. Well, I told you I was going to miss it. So, housekeeping, homework 5 is due Thursday, so you all know the drill. I always like the day before, see if you all have any questions. Are there any questions on homework 5? So you've already done it, right? You're finished with it? Everybody's like, he isn't going to look at me, right? He's not looking at me, right? I mean, I'll say this. I do recommend that you try and get a head start. And this is a little bit of a longer assignment, so please don't wait until Wednesday night at 9 o'clock to start this one. It's going to be a long night. Sound good? Okay, all right. So today I want to go through deflections in beams. What we do in here is a little different. If you're a civil engineer and you take structural analysis, the computation of beam deflections and the understanding of beam deflections is an incredibly important topic to us as civil engineers. I'm not saying it's not important to you mechanical engineers, but more often than not, there's a few other ways of going about it. I would argue maybe some simpler ways of going about it. But also, I would say that you mechanical engineers are probably dealing with simpler loading situations when it comes to beams than us civil engineers. So I'm going to show you 2 methods to compute beam deflections. And if you're in structural analysis, these are different than what we're doing in there. So you'll get a broader picture of things. Now, a couple of things I'm going to do here. So number 1, I'm going to make some assumptions. We're going to assume that the behavior of the beam is linear and elastic. We're also going to assume that plane sections remain plane, and I think we've already discussed that. Remember, you have the book, and you take the book, and you draw a line, and you bend it, the line remains flat, so we're going to assume that as well. We're also going to assume that deflections are considered small when compared to the original member lengths, and I'm pretty sure I discussed that with you all in here. I'll admit that between here and structural analysis, it gets a little fuzzy, but the easiest way to explain that is to imagine the scenario that I'm standing on top of a mountain, and let's say she doesn't like me very much and she decides to give me a shove. Well, that's one thing, but imagine if she does the same thing, but in this time I'm wearing an 80-pound backpack. It's a little bit harder to retain my stability because what happens is as soon as, here's me and I've got the 80-pound backpack, as soon as I get shoved laterally, well, it's not just a load, it's a load times a distance because that backpack is off my center of gravity, okay? That basically a bending moment, okay? That moment is going to cause me to fall over more, which is going to cause more moment, which is going to cause me to fall over more, which is going to cause more moment. It's going to kind of build on itself, right? That phenomenon is what's called a second order effect, where you have to consider the equilibrium of the structure once it's displaced, once it's deformed, okay? We are, in this analysis, considering a first order analysis. In other words, we don't have to go back and reconsider equilibrium of the displaced shape. You might ask, well, is that valid? Is that a reasonable assumption to make? It is when you have deflections that are really small, which in all honesty, in most engineering applications, that is the case. I mean, going back to a civil engineering example, if you have a bridge, let's say a highway bridge, okay, a very common deflection limit is L over 800, okay, L over 800. So to give you kind of an idea, that's a live load deflection limit for highway bridge design. So if you have a bridge that's like 40 foot long, take 40, or 480 inches, divide it by 800, so you're talking about that much, you know. A 40-foot long bridge can only deflect that much. That's pretty small, you know. Kind of makes sense. So small deflection theory is a reasonable assumption. Okay. Now, considering what we've discussed in here so far, and by now I think we have a pretty good understanding of beam bending theory, I think that this derivation is going to be pretty straightforward to understand. So I have a beam, and I have a beam that's been deflected some portion. So it's deformed. So it's not a straight beam. It's a beam that is curved because it has undergone some deflection. Okay? Now what I have here is the beam, and then this solid red line right here, this solid line, that is the neutral axis. That's where the centroid is. Now, if you recall from bending theory, the centroid experiences no bending stress, right? And then, you know, if you go, let's say, above the centroid, you might experience compression, and below the centroid, you might experience tension. But at the centroid, you experience no bending stress, right? Well, if you experience no bending stress at the centroid, I think it stands to reason you're not going to experience any strain or any deformation at the centroid. In other words, the neutral axis, the line along the centroid, remains the same length before as it did after, okay? In other words, once you deform the beam, the neutral axis remains the same length. Now, how long is that solid line? How long is the neutral axis? Well, we're going to assume that this is circular for ease of derivation. How long is an arc length? If you have an arc length of some radius and some angle, how do you determine how long that is? Well, it's the radius times whatever that angle is. Pretty straightforward, right? So that's what we would call the original length. Okay, that's the original length. Now, so that's initial length. The final length, the deformed length, is the length of this dashed line. So again, the solid line remains undeformed, but everything past that is away from the centroid, so it's going to experience some deformation. So in this image, this solid line is experiencing compression, so it's shorter. Okay, and how do you know that it's shorter? Well, here's the original length, and here's the final length. So we took the original length and we subtracted something. Okay. So how did we determine that? Well, it's the same way we determine this, a radius times an angle. The angle is the same, but the radius, it got subtracted some. How much did it get subtracted? Well, however far you are away from the centroid. Okay? So if L is the initial length and L prime is the final length, then the change in length is the difference between those two, which is just minus y theta. Well, if you know the change in length, and you know the original length, well, what is the change in length divided by the original length? That's the strain, right? So here we have the final length, here we have the initial length, so that's the change in length over the original length, that's the strain, and there we go. I think by now that should be a pretty straightforward derivation. Like, that's not too out there, right? Okay, everybody good? All right. Now, again, we're assuming linear behavior, we're assuming elastic behavior. So if the strain is a linear proportion, I mean, what do we have? We have, you know, if you want to think about it like this is a linear proportion. The farther away we get from the centroid, the bigger y is, the bigger the strain is. That's a linear relationship. Well, if that's linear, if the strain is linear, then the stress is going to be linear as well. And how do you determine the stress? Well, it's E times the strain. So we have a definition for the stress, okay? Well, how is that useful? How can we utilize that stress term in a means that makes sense? Well, I want to introduce this definition. Now, by now, I think that this should be a pretty familiar approach here in this course. I mean, how do we define moment across a cross-section? Well, we can define that infinitesimally by taking a little differential element, remember a little itty-bitty slice, a dA slice, and saying, well, the force on that slice is sigma dA, right? Okay, so sigma dA is the force. If we multiply that by y, it's a force times a moment arm, so that'll give us a moment, but that's just the moment on that little itty-bitty slice. If we integrate that about the area, that'll give us the moment, right? That's pretty straightforward, okay? Now, the only thing that might seem a little weird is, well, Dr. Mike, why do you have a negative in there? There's some negative sign just got thrown willy-nilly in there. Well, the negative sign, basically in a nutshell, comes from our sign convention. When we draw moment diagrams, we're using a sign convention that's really, really easy to follow. I mean, you look at the shear diagram. If you have positive area, you draw it up. If you have negative area, you draw it down, and it's pretty straightforward. But if you technically sort of go back to, y'all remember the right-hand rule, right? Remember that, and then moments go like that. If you technically go back to all those fundamental sign conventions for moments, we're technically using a backward sign convention when we draw moment diagrams. It's technically negative. So I'm throwing that negative sign in there just to bring everything back to a consistent convention. So that's all that is. I don't want you to think it's anything mysterious, because it's really not. All right? Now, if you've got that, what we can do is we can say, all right, here's my expression for moment, right? Well, I had already defined what stress was, so I'll plug that in, and then I'll factor out everything that's a constant. And then I'm left with an integral that looks like this. I have the integral of y squared dA. Well, what is the integral of y squared dA? We've already seen that before in here, right? The integral of y squared dA, that's the moment of inertia, okay? So, and I don't think that should be incredibly surprising that the moment of inertia pops up in beam deflection. I mean, it popped up in bending stresses, so it should be pretty reasonable that it's popping up here. So here I have this following relationship. So I have m equals E over rho times this integral, which is just the moment of inertia, and I get that box down there. And this is basically the relationship between moment and curvature. Okay, so we have, what do we have in this expression? We have the moment, we have the Young's modulus or the elastic modulus E, we have the moment of inertia, and then we have this term rho. Okay, and if you recall, rho was this radius right here. Rho was, if you have a deflected portion of a beam, rho was sort of that quantity defining the radius of curvature. Everybody okay with that? Now, here's the thing about the radius of curvature. Okay, now you all take a 5-hour Math 229 Calculus 1 course here at Marshall, and I know that they showed you a lot. Okay, a lot. And then after you leave that class, and it's, you get to be my age, where you took Calc 1, what was it? Oh, God, like 14 years ago. Oh, God, I'm getting old. And when you took Calc 1 a long time ago, it's been so long that there's only really few fundamental things that you remember when you take away from that class. Like, everybody in here should remember from Calc 1 how to take a basic derivative, how to take a basic integral, and what a limit is. But when you take that class, there's a lot of little things that you talk about that you might not remember. Like, what's the derivative of the tangent squared? Do you remember that formula right off bat, or can you use the product rule or whatnot to figure that out? One of the things that I promise you was probably shown to you in Calculus 1, and you just shown it and then moved on, was curvature. Okay. Now, to be clear, curvature is a little different than concavity. I think everybody in here probably remembers concavity, right? Because if you take the derivative, that will determine the slope of a function. If you take the second derivative, that'll tell you the concavity of that function. But curvature is another sort of special definition in and of itself. To determine the curvature of a function, if you have a function y, to determine the curvature, it's this expression here. And it's a little long, it's a little out there. I promise you, if you open up your calculus book, it's in there. Okay? Now, what we're going to do is use a little bit of reality when it comes to how beams behave, and let's see if this makes sense. Okay? Remember, go back to the bridge example. You're talking about a bridge that's like 40-some feet long. We're talking about deflections like that. Really, really tiny deflections. So again, we're talking about small deflection theory. So small y values. Okay? Now take that y curve and take the derivative of it, dy over dx. That's the slope, really, really tiny slopes. What happens when you take a really tiny number and you square it? You got a really tiny number, right? So I propose that this dy over dx squared term right here, that can go to 0. And if that goes to 0, you have the second derivative divided by 1 plus this to the 3/2, which is 0. So it's just the second derivative. Okay? Everybody see that? That if this fraction here, if this goes to 0, then you have our curvature is d squared y over dx squared divided by 1 to the 3 halves. Well, 1 raised to any power is itself, right? So that's just going to be 1, and then that's going to be this, okay? And once you get that, erase that. Once you get that, you can generate the following expression, which is arguably one of the most fundamental equations in all of mechanics, period. How many of you are in fluids? I'm just curious. Is anybody in fluids? Have you seen Bernoulli's equation yet? Okay, Bernoulli's equation is one of the most fundamental equations in all of fluid mechanics. That's one of the most fundamental equations in all of solid mechanics, is the relationship between moments and deflections in beams. This is sometimes called the Euler-Bernoulli beam deflection equation. Sometimes it's called moment curvature. This is pretty fundamental, pretty fundamental, okay? Now, everybody okay with this? Now, let me sort of take this slide and sort of digest it a bit. You can, because of this relationship, we can actually take loads and link them all the way to deflections and back again. For instance, how did we go from, let's sort of take what's over here on the right. How did we go from a load to a shear diagram? We basically integrated the loads to get the shear diagram, and then we integrated the shear diagram to get the moment diagram. So there's a relationship between loads and shears and moments and what have you. Well, now I can take that relationship and say, well, you know, up until now, all we've known is the relationship between loads, shears, and moments. Well, now we can take moments and relate them to curvatures, which can relate them to slopes and relate them to deflection. So we can take it all the way down, okay? And this relationship, what you see here on this slide, actually forms the basis of really oodles and oodles of different types of methods for computing deflection. And depending upon whoever teaches you structural analysis, sometimes structural analysis professors go through a lot of them. Like there's the unit load method, conjugate beam method, and all these different methods. I know when I teach structural analysis, I really only use one method because I'm trying to, you know, get the students the most bang for their buck. But in here, I want to show you a couple methods that are different. One of them is the double integration method. Okay. Now, right off the bat, I want to tell you that in order to utilize the double integration method, you really need a beam loading the scenario that's simple. Okay. You need something that's straightforward. So for you folks in structural analysis, an easy way of explaining it is if your beam can be defined by one moment function, this is fine. Whenever you've got multiple moment functions, don't use this, okay? Which is honestly more often than not in civil engineering land. But for us, it'll be pretty fine. So this method is the double integration method. It's sometimes called the direct integration method. So here's our beam deflection differential equation. If I want to solve for y, if this is the second derivative, we'll just integrate that twice. And bam, there's y, okay? And that is, in a nutshell, the direct integration method. It's that simple, okay? Now, the problem is these are not definite integrals. These are indefinite integrals. And when you integrate something indefinitely, what's the integral of x squared? Plus c, right? It's 1/3 x cubed plus c. There's an arbitrary constant of integration. Well, when you utilize the direct integration method, you are going to get arbitrary constants, and you have to determine those arbitrary constants. And we're going to determine those arbitrary constants using our boundary conditions, okay? So here's what I mean by our boundary conditions, okay? Let's look over here on the left, okay? So let's say I have a roller support or I have a pin support, okay? Anytime I have a roller support or a pin support when it comes to a beam, that is a scenario where the beam can freely rotate. So the slope or the rotation, you know, has a value, but the deflection is 0. Okay. So when we perform our integration, we might get the deflection here is 0, or the deflection here is 0, and that will be how we solve for our unknown constants. If we have a fixed end, it's a little different. Not only is the deflection 0, but the slope is 0, because remember, fixed ends prevent not only translation, but they prevent rotation as well. So we're going to need to know these in order to assess this. I'll be honest, we're not really going to do any frames in here, but I just wanted to show you that if you're dealing with a frame, let's say you have a fixed connected joint, well, however much those deform, if you have a fixed joint, we assume that they deform to the same angle, so the angles are the same. We're not really going to worry about that in here. Don't worry, we got some examples exploring this. It's not bad. Sound good? Now, the only other thing worth mentioning is units, and luckily I've made your life a little easier in here on the unit system. So typically when you perform a beam analysis, you know, like if we're talking about a beam, how long is that beam? Well, we usually say it's like 30 feet or 40 feet. What about the load on that beam? Well, we might say it's so many kips per foot, or so many, or so many kips, or what have you. However, when we look at moments of inertia, that moment of inertia is usually in like inches to the fourth, or the Young's modulus is in KSI. So the problem is there's a unit incompatibility. You know, you've got member lengths in feet, you have moments of inertia in inches to the fourth. Okay. Well, what happens is this: if you take deflection and you carry out generally what the units are, if you use this convention, which this is a very, very common convention with U.S. units, you got a little bit of a problem. Okay. When I compute deflection, I want deflections in inches. Okay. I want it deflects 2.6 inches down, or what have you. So we got to handle that. The nice thing about this method is that the unit conversions are actually pretty straightforward. If I take let's say the deflection, I have cubic feet per square inch. I need to convert each of these cubic feet, or each of these feet, to an inches. So there's 12 inches in 1 foot, but there's 3 of them, so I got to cube that. Well, what's 12 cubed? 12 times 12 is 144, times another 12 is 1728. So if I use this conversion factor with whatever I use for deflections, it'll generate an answer that's in inches. Okay? So 1728 is the conversion factor for deflections. Now, on the flip side, 144 is the conversion factor for rotations. But if you just use 144, that will generate an answer that's unitless. Okay? If we're talking about rotation, if we're talking about slope, here's a beam and how much did it twist, or how much is that slope, personally, I kind of like to see that answer in degrees. I think it's a little easier to understand. It's a little easier to visualize. So if you want to convert to degrees, if you stop right here, it'll be in radians. Well, there's 180 degrees in pi radians, and that'll get you your answer in degrees. Don't worry. This box right here, that's all you. That's pretty much where it is. That's it in a nutshell. Okay. Any questions? Okay. So I have a beam here, and forgive me. We're going to keep this a little symbolic. So forgive me. There is going to be some alphabet soup here, but I want to derive an expression for the slope and deflection of this beam, and then I want to show you something in your appendix so you can see where this stuff comes from. So I have a beam with that's simply supported, and it's subjected to a uniformly distributed load W. Okay? The beam has a constant E value and a constant I value, and I want to determine what the deflection is. So what's the deflection at some arbitrary point along the structure? Okay? So let's go ahead and solve this out. This is 25, right? All right, so here's the beam. Okay, so that's W. Now, one of the things I'm going to do right off the bat is I'm going to define sort of a coordinate system for me. So this is X, and this is Y. So what I mean by that is, here, let me do this. Let me do this. So. This beam is L long. So if you want to think about this in terms of a coordinate system, this point right here, this is the point on the beam where x equals 0. So you can think like x equals 0 or like x equals 1, 2, blah, blah, blah. This will be right here. This is where x equals L over 2, right? And then all the way over here to x equals L. Everybody okay with the coordinate system? So, okay. Now, we're going to have reactions here and right here. Does anybody know what those reactions are? Do we need to sum moments, or does anybody have an answer? You're close. Not W over 2, it's WL over 2. So that's a great point. So this is WL over 2. Because think, that W, that's sort of like 2 kips per foot. So if this beam was like 30 foot long, 2 kips per foot for 30 feet, that'd be 60 kips. So half and half would be 30. Okay, so that's where the L. That's an easy thing to get across. But remember, we can collapse that into a single point load that's WL. Okay, everybody all right with that? Now what I'm going to do is I'm going to cut a section at some random point right here. So what I mean by some random point is I'm saying that this distance right here, this distance is x. Okay? So if you want, although it doesn't really matter, I'm going to say that this distance is L minus x. Okay? Now I'm going to cut a section, and I'm going to cut a section and look to the left. And when I cut a section and look to the left, here's what I've got. All right. So this is WL over 2. This is W. This distance is x. And what I've got here, remember, when you cut a section, there's an unknown shear and an unknown moment. Now, I don't really care about the shear. All I really care about is the moment function. All right? Now, remember, we can collapse that into a single point load. What is that point load? If it's W over a distance x, what is the magnitude of that point load? No. It's WX. It's not a triangle, remember? It's just, think. Well, the moment's coming next. The moment's coming next. And you're close, but there's something you forgot. Because this is WX, and then this moment arm, what is that moment arm? X over 2. So you said WX over 2. It's not that. It's WX squared over 2. Okay. All right. So now if I sum moments at the cut, all right, so I have, at the cut, I've got WL over 2 times X. I have WX times X over 2, and then I have M. Okay? Now, did I go too fast with that? Is everybody okay with that? I'm summing moments at the cut, so I've got the reaction times X, the distributed load times X over 2, and then I have the moment. I don't have to worry about the shear because it's going right through the cut. Okay? Everybody okay with that? All right. So, chugging that out, I've got WL over 2 times X. Actually, here, let me rewrite it like this. Let me rewrite this. We say WL over 2 times X equals M plus W over 2X squared. And I have that. Is everybody okay with this? All right. If you're okay with that, then let's talk about this whole direct integration. All right. So which, by the way, if you hear me say direct integration method or double integration method, it's the same thing. I'm going to use those interchangeably. So, all right. So here's our expression. We have the second derivative is m over EI. Or if I want to rewrite this, I might say EI times the second derivative is m. Okay? You okay with that? So if that's the case, then I propose that EI times the first derivative, EI times the first derivative, which, by the way, that is just EI times the slope, is going to be the integral of m dx, which is the integral of that. Is everybody okay with that? I think if the second derivative is m, then the first derivative, I just got to integrate that. So let's take this one step at a time. Okay, we are integrating with respect to x. Okay, so let's take this term right here. WL over 2, that's a constant. So pull that out. What's the integral of x? 1/2 x squared. So could I rewrite this as maybe WL over 4 x squared? Would that be a fair way of doing that? I'll put that in parentheses. Minus, okay, what about this? We pull out the W2, or W over 2. What is the integral of x squared? It's x cubed over 3. So over 3, I maybe, what, W over 6 x cubed? Right? Did I forget something? Plus c. Now here's what I'm going to do. I'm going to say plus c1 because I'm going to have 2 of them. All right, so we're going to have an arbitrary constant of integration again. Okay, so this is our expression. So if you want to think about it like this is sort of our expression for slope. Okay, our expression for y, so EI y is going to be to integrate this again. Hence why it's called the double integration method, because you're doing it twice. All right. So again, take these one at a time. Let's take the first one. So you have WL over 4 times x squared. Pull out the constant, and then what's the integral of x squared? X cubed over 3. So that first term, maybe WL over 12? WL over 12x cubed? So minus, pull out the W over 6. Integral of x cubed is x to the 4th over 4, right? So W over 24, right? So W over 24, x to the 4th. Plus, what is the integral of C1? There we go. That's, see, you can see what happened. We're going to have C1x, but we're going to have another constant. So plus C2. Hence why, you know, you look in the crystal ball and you say, well, we'll call this C1 because we're going to have another one. Everybody okay with that? Now, if you're okay with that, then we've got to do some simplification, or we got to figure out what these boundary conditions are, or these constants are. How are we going to determine those constants? We're going to use boundary conditions, okay? Excuse me. All right, so boundary conditions. All right? I propose that right here is where x equals 0 at that left support. And at the right is where x equals what? L, right? Here's what I propose are my two boundary conditions, okay? So, first off, we need two of them. Why do we need two of them? Because we have two constants, okay? So I propose that for my first one, at x equals 0, y equals 0. What is y? Y is the deflection. Here's my beam. I sit on the beam. How much does it deflect? I propose that at that support, it doesn't deflect at all. Okay? So that would be my first boundary condition. So if that's my first boundary condition, what's my second boundary condition? There you go. There you go. Exactly. At x equals L, y equals 0. That's a Twitter handle right there. Hashtag boundary conditions. All right. I'm going to have my silly jokes. All right. So both of these are related to the y function. Okay? In other words, we don't need to really look at this anymore when we're trying to solve for the constants. And that's not going to be the case on the next example. Okay? The next example, we're going to have to go back to this one. So let me sort of rewrite my expression down here. So we have EI, oh, you all don't have to do this. I'm just doing this for posterity for me. EIY equals WL over 12 x to the third minus W over 24 x to the fourth plus C1x plus C2. Okay? So here's our expression, and we're going to use each of these boundary conditions to determine what those constants are. Let's start off with the first one. Okay? So the first one states that at x equals 0, y equals 0. Okay? So basically all that means is just plug those values in. So the first one, okay, let's take a look at our equation. We have EIY equals a bunch of crap. Okay? For our first boundary condition, what is y? 0. So this EIY term right there, that is 0. So 0 equals a bunch of junk. So what do we have? We have WL over 12 times 0 to the third minus W over 24 times 0 to the fourth plus C1 times 0 plus C2. What does that tell you? C2 is 0. So there's one of them. Pretty straightforward, right? So there's that one. Now let's do the remaining one. All right, so what about the second one? I think I got room here. So we have 0 equals, we have WL over 12 times L to the third, right? Minus W over 24 times L to the fourth plus, now we have C1 times L plus C2, but we know C2 is 0, so I ain't going to worry about it. All right, so what do we have? WL to the fourth over 12 minus WL to the fourth over 24 plus C1 times L, right? So can we simplify this? What is 1/12 minus 1/24? You have Casio FX115 ES pluses. It will do this for you. So WL over 4th over 24 plus C1L. I propose then that C1 is minus WL to the third over 24. Now how did I get that? So if I divide everything by L, 0, C1, and this is WL to the third, then subtract it over, right? There you go. So there's C1, there's C2. There you go. All right. Does everybody have this? So here, I'm going to copy that because I'm lazy. There we go. Now, what was C1 negative? So minus, and then that was WL to the third over 24 times X, right? So that's our expression. And then if you want, what you can try and do is maybe simplify this a bit. So how about this? There's a lot of W's, a lot of 12s. Maybe, bless you, maybe we can factor that out a bit. So we've got, let's see, we can factor a W out. We can factor a 12 out. And what do we have? We have LX to the third minus W over 2, or no, X to the fourth over 2, right? Minus, and then what do we have here? We have L to the third over 2 times X. Did I do that right? We could also probably factor out an X, WX over 12 times LX squared minus X to the third over 2 minus L to the third over 2, right? And bam, that equation will tell you what is the deflection in that beam due to a uniformly distributed load. If you want, we can sort of rewrite that. We can say EIY or Y of X equals WX over 12 EI times LX squared minus X to the third over 2 minus L to the third over 2. What do you think?
In the previous slide, we said that the slope equals 0 at one of these, like just regular support.
No, at a fixed support. At a fixed support. In other words, here's this problem. Here's the next problem. I propose that for this problem, the slope equals 0 at A, but not here. Because the beam is going to deflect something like that. So this obviously, like that isn't a 0 slope. There's an angle there. In fact, that's where the maximum angle is. Make sense? Everybody okay with this? Now, just so we're aware, let me show you something. If you go to your textbook, okay, and you go to Appendix H, Appendix H lists slopes and deflections for various common situations. Look at situation number 1 for H2. Look what we have here. Look at this expression right here. If I can draw. There we go. I'm trying to box it. There we go. Look at this expression right here. Look at what the book has versus what we got. Okay? Let's take a look at that. Well, The only difference is they factored out a 12, or a 24 as opposed to us factoring a 12, and they threw a negative in there. Why did they throw a negative in there? Because they wanted to express that the deflection is going downward, but it doesn't really matter, okay? But in the end, that's the exact same expression that we got. Everybody okay with that? Now, how did we get this expression right here? Just take the derivative of that, because that's the slope. How do you get the maximum deflection? Well, there's a couple ways of going about that. How do you get the maximum deflection? Well, how do you determine the maximum point on a curve, right? You take the derivative, set the derivative equal to 0, right? Once you find where the derivative equals 0, plug that into your function. That'll give you your maximum or minimum, right? Or we could be engineers about it. This is simply supported being with the uniform distributed load. Where is the maximum deflection? Right in the middle, right? At L over 2. So if you plug in L over 2 right here, what do you get? Well, let's see. So we have W over 12 EI times L over 2 times, and what do we have? We have L over 2 squared minus 1/2 L over 2 cubed minus L cubed over 2. So this just becomes a little bit of alphabet soup. So let's see what we've got. All right. On the outside, we have WL over 24 EI, right? On the inside, so this first term, we have L over 2 squared, so that's L squared over 4, L cubed over 4, minus, okay, we have L over 2 cubed, so it's L cubed over 8, times 1/2 is L cubed over 16, minus L cubed over 2, right? So if I want to factor the numbers out, what I have is this, is I have WL over EI times 1 over 24, and then actually hold on, let's redo this. Is there a common term in the brackets that's easy to factor out? L cubed, right? So if I have L cubed factored out of this would be WL to the 4th over EI, over 24 EI. And so that's EI. And then we have 1 over 24 times 1 over 4 minus 1 over 16 minus 1 over 2. Can anybody tell me what that fraction is? Your Casio should be able to just compute that fraction directly and like leave it in a fraction format. Well, but then there's 24. Now times the 24th. And that's what they got right here. Now they're using Q instead of W, but there you go. Not too bad, right? So how would we determine the maximum slope? Well, take the derivative and plug in x equals 0. Or plug in x equals 0 or x equals L. In fact, if you do both, you're going to get the same answer, just opposite signs, because one's going to be rotated like this and the other's going to be rotated like that. Because you know, if it deflects like this, one's going to go that way and one's going to go that way. So equal and opposite signs, or equal magnitudes but opposite signs. Sound good? Now, as for a quantity, how do we determine the quantity? Well, let's go back to the example. The example says determine the maximum slope and deflection. I'm just going to worry about deflection. You all can do slope on your own. Determine the maximum slope and deflection based off these following values. So we have an E of 29,000, I of 1,500, L of 30 feet, W of 2. So what I can do is this. Therefore, for our beam, Y max is, here's what I'm going to do. Minus 5 times our W. Our W is 2 kips per foot. Our L is, in this case, 30 feet, so that's 30 to the 4th over 384 times E, which is 29,000, times I, which is 1,500. But if you notice, I'm being pretty fast and loose with units. I'm not even really bothering with it. And the reason why is because I already have a unit conversion computed. When I'm determining deflection, I multiply that by 1728. And that will generate all the unit conversion that I need. Okay, so when you convert that out, what does our units come out to be? Like, what is that? Or I'm sorry, not our units. What does that value come out to be? Do I have a second on that value? Okay, and so that's going to be inches, or Y max is 0.838 inches down. What do you think? Sound good? Now, that's for deflection. For slope, what do we do for slope? Well, everything we do for slope is the exact same thing. We go back a slide, and we say, all right, here was our expression for slope. It was EI times theta is WL to the 4, or WL over 4 times x squared minus W over 6 times x cubed plus C1. We have that expression for C1, plug it in, plug in our values, and then our conversion factor isn't 1728, it's 144 times 180 over pi. Okay, and remember, our maximum slope is going to be either at x equals 0 or x equals L. I mean, take that expression, plug in x equals 0 or x equals L. You're going to get the same value but opposite signs. Okay, promise. Sound good? All right. Any questions? All right.
So can we use this method if we don't have a continuous flow to plot across the trajectory across?
That's a good question, and the answer is yes, but it gets a little crazier. And the reason why is this. You have different moment functions, right? So not only do you have to satisfy the constants of integration for the boundary conditions, but you have to satisfy constants of integration related to the continuity. In other words, the slope and deflection where those two curves meet have to be the same. And the algebra gets nasty. I'm not saying it's not doable. It's very doable. It just gets very nasty. And so as a result, engineers, and particularly civil engineers, have developed oodles and oodles of different ways of getting about that. For example, if you have a beam that has a bunch of point loads on it, so you got a beam, you got a point load, point load, point load, point load. You could have 7 or 8 different moment functions, and this method would be horrendous, with that approach. There is another graphical approach that you can utilize. It's called the conjugate beam method, and I don't want to confuse you or get too far down that road, because I really think it's outside the scope of what we care about in here. But it's a crazy method, because what you do is you take the beam, you draw the shear diagram, and you draw the moment diagram, and then you take the moment diagram and you actually put the moment diagram on the beam as if it was a load, and then draw the shear diagram, moment diagram for that, and that's your slope and deflection. But way outside the scope. So there's a couple other caveats for that. You have your real beam, and then you have to generate what's called a conjugate beam. So if you have a fixed end, it turns into a free end. If you have a free end, it turns into a fixed end. It's a little involved. What we do in structural analysis is a unit load method, and it's basically related to the structure's energy. It's like a law of conservation of energy approach. Energy in equals energy out. And my structural analysis folks can tell you all about it, right? So it's easy, right? You just got to have good bookkeeping. So, but yeah. Any questions? All right, let's talk about housekeeping again. What are you giving me on Thursday? Homework 5. What am I giving you on Thursday? I'm giving you homework 5 solution. I'm hopefully giving. That was a nice try. I'm giving you the solution to homework 5, and I'm hopefully giving you back your copies of homework number 4. Okay. We are going to have an exam review on homework or on exam 2 on Thursday. The slides are there on Blackboard. I highly recommend that you take a look at them. I highly recommend that you review them. I highly recommend that you come on Thursday prepared to ask questions. Again, remember how those review sessions go. We could be in here for 5 minutes, or we can be here the whole time. It's really up to you. It's not up to me. And with that, I think I'm going to end early. We could start our next example, but we're not going to get back to it until like a week and a half from now. And I don't see the point, really, and I don't see the point. So if I'm of the opinion, let's just wait and do that example when your exam is over. So Thursday, come with your homework and a load of questions. That's all I got. A load of questions. Heck, no, that was pretty. I didn't mean for it to be, but see, the best one was last year when I was when everybody found out I was having a daughter. They thought I was going to name her Bridget. I said, I'm not doing that to her.